In this lesson, we're going to look at how to solve equations making use of logarithms. So if we have a look at the work we've been doing so far to do with exponentials and logarithms, we started with sketching graphs of what the exponential functions look like. Then we talked about e to the power kx and why that was important. Remember, that was the special base number that occurs in nature to do with exponential growth and decay. We used and interpret models using exponential functions and saw how useful they were. Then going on from exponentials, we looked at logs, which, if you remember, the link between exponentials and logs, they're effectively the reverse of each other. And then we looked at log laws, which tied in with the laws to do with exponential functions. So when you multiply them, you add the indices, that sort of thing. So what we're going to look at today is a variety of different equations that either contain logs or can actually make use of logs to solve them. So let's have a look at the first couple of examples. So these are quite straightforward ones here. So they're not ones where you can naturally look at them and come up straight away with the what the answer was, because if I had something like, 3 to the power x equals 9, you could look at that and you could very easily say, well, x is 2, that's easy. These ones, if you have a look, it says solve the following equations giving your answers to 3 decimal places. Now, to solve something like this, what we've got to remember is what's down at the bottom of the slide here. So the link between the fact that if we've got 10 raised to the power 2 gives 100, the equivalent log form of that equation is that log to the base 10 of 100 is 2. So remember, when we're looking at a log form here, if we want to work that out, we're saying what power do I raise the base number 10 to get 100, and that gives me 2. Okay, so if I go back up to my first example here, what I'm saying is x is equal to what power do I raise 3 to get 20. So if I write that in my equivalent logarithmic form, x is equal to log. Now remember, the base is always the big number. Okay, so that's the number for this particular one, that's going to be the number 3. So it's log to the base 3 of 20. Because we remember what that log to the base 3 of 20 means. What you should be asking yourself is, what power do I raise the base 3 to get 20? Now, the use of being able to write it in this form is that then you can grab your calculator and your calculator will tell you what the answer to that is. Now, you can probably work out roughly what it's going to be, because if you think 3 squared is 9 and 3 cubed is 27, so it's going to be between 2 and 3, so it's going to be 2 point something. So it's a good idea to have a bit of an idea as to what your answer is going to be. Now, if you go and reach your calculator, we should know from previous stuff that we've done that my log button is beneath my integration button. So if you press the log button, the first thing you type in is the base number, so you type in 3. You then need to use the right arrow, type in the 20, press equals. Now the question has asked me for 3 decimal places, so round it carefully, 2.72, and then it's 7268, so that's going to be to 3 decimal places, so that's 2.727. So as expected, somewhere between 2 and 3. Okay, let's do the same for this next one. Now we're going to do the same kind of thing, but we can just see that our power there is slightly more complicated. So what we're going to do when we write our equation down, instead of just writing x as the power, it's 4x minus 1. Okay, now remember our log form. It's log. Now the base is always the big number that's raised to the power. So log to the base 5 of 61. Okay, so remember, your calculator will tell you what the answer is for that. What I'm going to do before I reach for my calculator is just do my rearranging. So what I'll do first is I'll say that that's equal to log to the base 5 of 61. And then I've taken the plus 1 over the other side. And then just to get x on its own, I'm going to do log to the base 5 of 61 plus 1. And then I'll put all of that over 4. So I'm going to show my working and do my rearranging before I reach for my calculator. Then reach for your calculator, use the fraction button, type in your log to the base 5 of 61. Again, we could work out roughly what that's going to be because 5 5s are 25 and then 5 cubed is 125, so it's going to be between 2 and 3. Put that into your calculator and then round it to 3 decimal places and we should get 0.889. Okay. When you are solving equations, as always, it's good to be able to sort of put them back into your original equation just to check that it works. Now we have rounded, okay, so if I put in 5 to the power of 4 times my answer, 0.889, minus 1, okay, and press equals, I get 61.17, so it's pretty accurate. Obviously it's not exactly 61 because of my rounding, but it's a good idea to put it back in just to check that it works. Okay, let's go on then. Right, now this next one. Examiners love questions like this, and you might look at it and think that looks very different to anything that you've ever seen before. So when you're presented with something new and something different, what you want to do is you want to have a look at it and think, have I seen anything that looks like that before? Okay, so I've got an equation. The equation's got 3 parts to it. So I've got a constant here at the end. I've got minus 12 times something. I mean, that's 5 to the x at the moment. Okay, and then at the front here, I've got 5 to the 2x. But if you think about that, if you relate this 5 to the 2x to the 5 to the x, well, that is actually 5 to the x all squared. So if I have a look at the form of that equation, it's actually a quadratic equation because it's got something squared minus 12 times the something and then plus 20 equals 0. So you have to be able to spot that this is actually something that's called a hidden quadratic. So it's a quadratic equation, but it's not just a quadratic equation in x, it's a hidden quadratic. Now what you can do, there's a couple of different ways of solving these. So I'll show you one way, which quite a lot of people like, is to actually make it look a little bit more like a quadratic by using a substitution and saying let y equal 5 to the power x. Okay, so let y equal 5 to the power x. Now if I do that, let's see what my equation becomes. Well, if y is 5 to the x, then 5 to the 2x is going to be y squared because of what we talked about here. Okay, minus 12, 5 to the x is y, plus 20 equals 0. And a lot of people like to put the substitution. Do state clearly what your substitution is. Put my substitution in and then rewrite it to look like that. Now that looks a bit more familiar as to something you can solve. Usually these ones, to be honest, will factorise. So hopefully you can see that that will factorise as y minus 10, y minus 2 equals 0. So I get 2 answers for y, so I get y equals 10 and I get y equals 2. Now do remember, we've then got to work out what the value of x is because my original equation didn't have y's in, it had x's in. So now I've got to replace back in my substitution. So y equals 10 is equivalent to saying 5 to the x equals 10 and y equals 2 is equivalent to saying 5 to the x equals 2. Now we're back to ones that looked very similar to the ones on the previous page. So what we've got to do now is write those in the equivalent log form. So 5 to the power something equals 10. So that tells me that my power is log to the base 5. Remember, it's always the base number of 10. So x is equal to log to the base 5 of 10, because remember what we say here is what power do I raise 5 to get 10? Okay, now again we can work out that's going to be something between 1 and 2, because 5 to the power 1 is 5, 5 to the power 2 is 25. You pop it in your calculator. Do look at the question. 3 significant figures, so do make sure you give it to the accuracy they've asked for, otherwise you won't get the marks for it. So that's 1.43, so that's one answer. Let's look at the next one. 5 to the power x equals 2. Let's write it in our log form. X equals log to the base 5 of 2. Okay, put that in your calculator. We can work out that's going to be between 0 and 1. So to 3 significant figures, 0.431, like that. Okay, and again, you can just take a moment, you can take those values, we can substitute them back into your original equation up here. If you've got time in your exam, substitute them back in, and then just check that they roughly give 0. Rounding means it won't be exactly 0, but it should be roughly 0. Okay, right, now that using the substitution, that's a completely valid method. I'll just show you some people, once they've spotted that that's a quadratic, rather than actually using a substitution, they are able to go straight to saying, I know it's a quadratic in 5 to the x, so they factorise it with 2 brackets with 5 to the power x in. They see that it's needs to have a -10 and a -2, so then they get straight to this line just by factorising like that. That is completely valid. Okay, I think sometimes the questions ask you to use substitution and show that that equation reduces to an equivalent quadratic, in which case you have to do that. If you can go straight from that to that and you're very happy with doing that and you can get it right every time, then that is a completely valid method as well. Okay, so really up to you with that. Do show your working now. Okay, right, let's just do one more similar one to that one. Okay, now you'll notice it is similar to the first one, but there's something a little bit different, and the thing that's a little bit different is the power that we've got here, so the power for 3. So you should notice it is again a hidden quadratic, but we've got a -9 here, we've got a 3 to the x here. So at the front here, really, we should only have a 3 to the 2x, not a 3 to the 2x plus 1. So what we need to do is use our knowledge of index laws to rewrite that. Now, 3 to the power 2x is the same as 3 to the power of 2x times 3 to the power 1. So 3 to the 2x plus 1, remember what you do when you times, you add together the indices. Okay, so make sure you're happy with that. So what I can then do is I can rewrite my equation as 3 times 3 to the 2x, okay, minus 26 times 3 to the x, minus 9 equals 0. Okay, so now it's looking a little bit more like the first one that we did, the only difference being we've got a 3 at the front here. Let's use our substitution. Let y equals 3 to the 2x. I think when you've got the slightly more complicated ones with a number in front of the quadratic part, I think the substitution does make it look a little bit easier. Oh, hang on a minute. That's not right, my substitution there, okay? My substitution, cross that bit out, my substitution should be let y equals 3 to the power x. It's always the bit that's in the middle. Okay, so then my equation becomes 3y squared minus 26y minus 9 equals 0. Okay, so do make sure you get that substitution right. It's always the middle part, okay, is equal to y. Right, now That does again factorise. If you struggle to factorise, you can sneak it into your calculator as a quadratic equation and see that the answers it gives you are minus a third and 9. So then you should be able to write the brackets according to that. You do need to show you're working for it though, so do make sure that you write out the factorised form even if you use your calculator to help you. Right, so again, I've got two answers here. They're answers for y. I've got to put my substitution back in. So 3 to the x is minus 1/3, or 3 to the x equals 9. Now this question highlights a very important point here. Sometimes you get answers that don't work. Okay, this here is basically impossible. So when I do these questions, I would write it down as an answer. I would put a line through it and say impossible. Why is it impossible? Well, remember your graph of 3 to the power of x, it's always positive. Do you remember what your graph looked like? It looked like that, never went below the x-axis. So it's always positive. So that doesn't give me a valid answer. This second one here, okay, I could write it in my equivalent log form, but I think all of us can look at that and realise that 3 to the power what is 9? Well, x is equal to 2. So if it comes out as a nice answer, then you just write it down as a nice answer. Okay, so I think that question has highlighted to you. Do look out for when you've got powers that are not just a 2x, okay, that they've got an extra part to them, then you need to split them like that. Make sure you look out for them. Okay, one more type of equation that you can get, and this really is making use of logs as a technique for solving equations that have the unknowns in the powers. Okay, you'll see the difference with this equation that we've got here. We've got a base number 3 on the left-hand side, and we've got a base number 2 on the right-hand side. So I'm not just immediately going to be able to write them in terms of logs to the same base. Okay, so if we remember some of our log laws, what we can do with this equation, a completely valid method, in the same way as a valid method is to square root both sides, square both sides, add 1 to both sides. A good mathematical technique you can use when the unknown is in the power is to take logs of both sides. Okay, so let's take logs of both sides. So I'm going to write log 3 to the power x equals log 2 to the power x plus 1. Now notice, I haven't written a base number next to my log. If you ever see log with no base number written next to it, log with no base number is log to the base 10. And we generally, as a rule, will use this when we're taking logs of both sides as a technique to solve the equation, but we're not bothered about the base. Okay, you have got log on your calculator, just an log on its own. It's basically, if you see where your shift button is, it's shift and then 3 buttons below it. So it's got the little, it's on your calculator, it's the shift and then that function there. So if you do that, that gives you just log, and that's log to the base 10. Now you might look at that and think, well, why was that useful? Remember our log law to do with a power. When we had our log laws, if we had a power, we could bring it down to the front. So I can write this as x log 3. We did quite a lot of that in our last lesson when we were simplifying expressions involving logs. So I can bring it down to the front. Okay, I can do the same with this. Now do be careful, because I've got x plus 1. I must stick it in a bracket. That's x plus 1 log 2. So what I've done is I've brought the powers down to the front. okay, and I can do that because of my log laws. Now, ultimately, what we want to do now with this equation is to rearrange it to get x equals something. Now, do remember log 3 and log 2 are just numbers. Your calculator will tell you what they are. So solving an equation with x's on both sides, what I want to do is get all of the x's on one side and all of the non-x's on the other. So what I'm going to need to do, so that should be log x log 3 equals, what I'm going to need to do first of all is to multiply out this bracket, because part of it has an x in it and part of it doesn't. Okay, anything involving x's, so that's that bit and that bit, I'm going to put over on one side. So I've got x log 3 minus x log 2. And I'm going to leave this over on the other side because it doesn't have any x's in it. Remember, log 2, just a number. Here's the bit you need to remember. I then take out x as a factor. X log 3 minus log 2. I know it looks really complicated, but do remember these are all just numbers. Log 3 is a number, log 2 is a number, log 2 is a number. And my final step, okay, I've not reached my calculator yet. Okay, because what I'm going to do now is reach my calculator, put it in as a fraction. Remember where your log button is, type it in carefully. Back to my question, 4 decimal places. Do look for the accuracy that the question is asking for, otherwise they will knock marks off. Put that carefully into your calculator and you should get 1.7095. Okay, just one answer for that. Now again, always good to be able to check your answers. You can take that and you can put it back into your original equation here. You can do 3 to the power of that. You can do 2 to the power of that plus 1, and they should be roughly equal to each other. Remember, with rounding errors, they won't be exactly equal, but they should be roughly equal, and that will check that you've not made a mistake in your working. Okay, so that question's really shown you the use of logs, that you can, when you're solving equations, if you have unknowns in the powers of the equations, okay, take logs of both sides. Just use log to the base 10, that's absolutely fine. Use your log laws to bring the powers down to the front, and then rearrange all the x's on one side, all the non-x's on the other. Okay, so make sure you're happy with that. Right, questions for you then. Okay, so exercise 14F, page 325, it's basically all of the questions. So what I want you to do, please make sure, write out the question first, show each of the steps clearly, like we have in the examples there. Check what the question is asking you for as far as accuracy goes. Now, I do want some of these questions submitted via Insight, not all of them. Questions 4, 5 and 6. Now, what I would like you to do, it's a lot easier for me if I can just go onto Insight and look at a single page of answers, have a look at them and then just give feedback. Okay, when it's on multiple pages, it's a bit more work for me to look at and to mark. So can you please fit them on a single page, upload it onto Insight, deadline by Thursday the 30th of April. The reason I'm saying by the end of Thursday is I will mark them, okay, I will put feedback on Insight, and then we will have our weekly Teams meeting on the Monday at 11 o'clock as usual, and then I will go through answers and also feedback anywhere that people had any problems. So I want them in, please, by the Thursday to make sure I have time to mark them on the Friday before I then meet with you on the Monday. So hopefully that will make sense. Okay, right, well, good luck with those, and I shall see you in our next meeting. Thank you.